Hello everyone, I am Devayan Ghosh, a student of 4th year BTech in Electrical Engineering. Today, I am here to give my BTP presentation. The topic of my project is coexistence of LTE and Wi-Fi technologies using MDPs and Reinforcement Learning. It comes under Communication Networks. I am doing this project under the supervision of Dr. KP Naveen sir. First, I would talk about the abstract of this project. The demand for mobile data is ever increasing in today's world. To tackle this demand, a novel idea of LTE unlicensed is put forth, where LTE networks are allowed to use the unlicensed spectrum. However, the performance of the already existing Wi-Fi networks in these unlicensed bands should not be degraded. In other words, both LTE and Wi-Fi should coexist with one another. In this work, we propose a time-sharing based approach in order to achieve coexistence between the two networks. For this, we have modeled both the LTE and Wi-Fi users as MM1 queues. Then, our problem in hand is formulated as a Markov decision process. Using queue learning techniques, we have tried to find out the optimal airtime values for each time frame. Finally, extensive simulations have been conducted to find out the efficacy of our proposed algorithm as well as to compare the results obtained through other non-learning based approaches. Now, I would give a brief introduction of my project. In CSAT or Carrier Sense Adaptive Transmission, the entire time is divided into several time frames of equal duration. In each of these time frames, LTE transmits in some fraction of time while the remaining portion of the time frame is utilized by the Wi-Fi devices. Now, it is to be decided that how much fraction of the time frame should be allotted to LTE and how much to the Wi-Fi. For this, we have made use of Q-learning based model to find the optimal air time. Now I would explain the problem statement. The aim of this project is to ensure coexistence of LTE and Wi-Fi technologies using MDP and reinforcement learning, or in other words, to enable access to LTE operators to use the unlicensed spectrum without severely degrading the performance of Wi-Fi devices. Some of the softwares or concepts that are required for this project are as follows: Python or MATLAB to simulate the MM1 queues and display the costs incurred for different policies, Markov decision process, reinforcement learning or Q learning to learn the optimal airtime, probability and statistics. Now I will talk about the procedure. First, I will mention the steps that I have followed till the mid-sem. To understand the concepts involved in a Markov decision process, to figure out the minimization functions and the constraints that are to be satisfied. Model the LTE base stations as MM1 queues. Plot the queue length versus time for a single LTE. Consider two LTE base stations and let them operate for 50% time each. Plot the queue length versus time. Next, I would talk about the work that I have done after the mid-sem. Repeating step 5 from the previous slide by exchanging one of the LTE base stations with a Wi-Fi access point. Train the network to learn the optimal time slots for LTE and Wi-Fi transmissions using Q learning. Compare the performance of the Q model with the other policies. They are constant action and random action based policies. Now I will briefly talk about the steps that are to be followed in future to complete this project. Increase the number of LTE base stations and Wi-Fi access points in the network. To vary the number of parameters such as discount factor gamma, exploration probability, epsilon, etc. and to observe the results. Now I will talk about MM1 queue. An MM1 queue is a stochastic process whose state space is the set given by 0, 1, 2, 3 up to all integers, where the value corresponds to the number of customers in the system, including those who are currently in the service. Arrival times have exponential distribution with parameter lambda and from state I to I plus 1. Service times have an exponential distribution with rate parameter mu. A single server serves customers one at a time from the front of the queue according to a first come first served discipline. When the service is complete, the customer leaves the queue and the number of customers in the system reduces by 1. The buffer is of infinite size, so there is no limit on the number of customers it can contain. Now I would explain about Q learning. Q learning is a type of reinforcement learning in which an explicit model is not required to solve an MDP, Thus, in Q-learning, it is not required to know the state transition probabilities. The Q-learning algorithm is based on a Q function that is updated whenever it receives a reward from a state transition after the agent takes a certain action. The update equation for the Q table can be seen in the screen. Here, alpha is the learning rate, gamma is the discount factor, and R is the reward. S is the state of the system, and A is the action taken by the agent. We have performed the simulations for 4 different policies, namely constant action, random action, Q-learning initial phase, and Q-learning steady phase. Now let's briefly look into these policies. Q-learning initial phase, or QLIP. In this policy, the Q matrix values are initialized to 0 and are learned gradually. In other words, these Q matrix values are updated after each frame time. This is the learning phase of the Q-learning algorithm. Q-learning steady phase. In this policy, the Q matrix values are obtained from the updated Q values from the previous step, that is QLIP. This is the testing or implementation phase of the Q-learning algorithm. Constant action. This policy is a simple one which uses a constant value of beta. In our case, we have taken the constant value as 0.5. Random action. This policy chooses an action randomly from the available set of actions. Discounted cost is given by the following recursive formula: j of k equal to j of k minus 1 plus nk plus mk into gamma raised to the power k minus 1. Here j0 equal to 0 and nk and mk are the lengths of the LTE queue and Wi-Fi queue respectively at the time frame k. Now let's discuss the simulation results. This plot on the screen shows the number of LTE users and Wi-Fi users in their respective queues with respect to time frame for a constant action policy, that is beta equal to 0.5. The arrival rate for both the queues are taken as 1, while the service rates for both of them are taken as 10. The length of both the queues could be seen to not to shoot up to infinity because in both cases service rate is greater than the arrival rate, or in other words, mean service time is less than the mean arrival time in both cases. In this plot, it can be seen that QLSP gives the best performance across all time frames as compared to the other 3 policies. QLIP doesn't give good results because the Q values are initialized to 0 and these values are updated eventually. While for QLSP, the updated Q values from QLIP process are used. Similar analysis could be given as the previous slide for the average discounted cost for different actions. Here the only difference is that the discounted cost is computed for 20 iterations and the mean is shown in this plot. Some of the conclusions are as follows. In order to handle the excessive demand for mobile data, we first proposed an idea in which the LTE operators could be allowed to use the unlicensed spectrum. In other words, it has to be looked upon that LTE and Wi-Fi technologies coexist with each other. For this very purpose, we first modeled the LTE and Wi-Fi users as 2 separate MM1 queues. Then, this problem is reduced to an MDP problem. The state of the system at each time frame k is given as nk, mk, where nk is the number of LTE users at time frame k and mk is the number of Wi-Fi users at frame k. Since MDPs could be solved using reinforcement learning, we have proposed a Q-learning based approach to find the optimal frame time matrix, which does not require the knowledge of intermediate state transitions. Finally, the simulation results showed the comparative analysis of the Q-learning based approach to the other 2 approaches, that is constant action and random action policies. These are some of the references that I have used to make these slides as well as they have been useful in my project. So I would like to end my presentation here. Thank you to all of you for patiently listening to my presentation. I would specially thank Dr. KP Naveen sir for helping me throughout this project.